A non-uniform electric field given by the equation shown here on the screen. Electric field equals 4I minus 3 times y squared plus 2 unit vector j in newtons per coulombs, pierces a Gaussian cube of edge length 2 meters and position as shown in the figure below. In the first part of the problem, we need to calculate the electric flux through the top, bottom, right, left, and back face. So let's start with the first part of the problem. We want to calculate the electric flux through the top face of this cube. Remember, electric flux depends on the electric field and the area through which this electric field is passing. In this case, we have a non-uniform electric field given by this equation, and we need to figure out the area of the top surface. Well, the top surface is a square, and the area vector associated to it will be oriented vertically upward. We need to calculate the flux as the integral of the electric field over the area of the top face. In order to calculate the integral, the first thing we will do is evaluate the dot product. We know that the electric field is given by this equation, and for the top face the area vector is oriented in this direction. Therefore, we can write the area vector as its magnitude dA multiplied by the unit vector j, because the area vector is along the y-axis. So the unit vector for the y-axis is the vector j. All we have to do now is take the dot product between the electric field and the area. I would like to remind you that the dot product between unit vector I and itself, or unit vector j and itself, or unit vector k and itself, according to the definition of dot product, is calculated as the magnitude of the first vector, which is 1, multiplied by the magnitude of the second, which is also 1, multiplied by the cosine of the angle between them. Well, the angle between a vector and itself is 0 degrees. So every single time we take the dot product between the unit vector I and itself, or j and itself, or k and itself, we get 1. When we take the dot product between two unit vectors that are perpendicular to each other, ij, ik, or jk, the dot product of those two vectors will be 0, because the angle between them is 90 degrees, and therefore when we have cosine 90, that gives us a value of 0. So now if we go back at the dot product between this vector and this vector, what you have to realize is that when you multiply 4i with dA unit vector j, that will give you a value of 0, because you're taking the dot product between the unit vector I and unit vector j. The only thing that we have left is the product between minus 3 times y squared plus 2 and dA. j dot j gives us 1. So the value of this dot product will be equal to minus 3 multiplied by y squared plus 2 multiplied by dA. Now if you look at this result, for the top surface, the y value is 2 meters. Every single point on this surface is at a distance of 2 meters along the y-axis. And if we replace the y equal 2 meters in this expression, we have that the dot product between the electric field and the area is equal to minus 18 dA. All we have to do is plug it into the integral, and we will have that the flux through the top equals minus 18 dA, which is equal to minus 18 integral of dA, where integral of dA is nothing else than the area of the top surface. And the area of the top surface is nothing else than the length of one surface squared. It is a squared. Therefore, the flux through the top surface will be minus 18 times the length of a side squared. The length of a side is 2 meters, and therefore the flux through the top surface will be minus 72 newtons meter squared per coulomb. Now let's find the flux through the bottom surface. For the bottom surface, the area vector is oriented down, and therefore we can write it as dA multiplied by minus the unit vector j. So the area vector is still oriented along the y-axis, but in the opposite direction. Again, we take the dot product between the electric field and the area vector. And again, you have to remember that when you take the product between this first term and dA minus j, you're going to get 0. So all you have left is minus 3y squared plus 2 multiplied by minus dA. That gives me a plus. And the result is 3 times y squared plus 2 times dA. Very similar to what we had previously. For the bottom surface, every single point on this surface has a y coordinate equal to 0. So this bottom surface, y equals 0, makes the value of this dot product equal to 3 times 2, 6 dA. We plug this into the integral, and the flux through the bottom will be equal to integral of 6 dA, where integral of dA once again is nothing else than the length of one side squared, which is 2 times 2, that's 4, multiplied by 6. We get that the flux through the bottom surface of this cube is 24 newtons meter squared per coulomb. How about if we find now the flux through the right surface? Well, in this case, the area vector will be oriented perpendicular to the surface and away from it, which means that the area vector can be written as its magnitude multiplied by the unit vector I, because the area vector is along the x-axis. Again, we take the dot product between the electric field and the area vector. And now what you have to realize is that when we multiply this term that has the unit vector j with the area vector that has the unit vector I, that will give us 0. So the only thing we have left is 4 times dA. Therefore, the flux through the right surface will be integral of 4 dA or 4L squared, and that gives us a value of 16 newtons meter squared per coulomb. When we calculate the flux through the left surface, the only thing that will be different is the direction of the unit vector. In this case, the unit vector will be oriented to the left. Therefore, you have to write it as dA times minus unit vector I. And we will have that the flux through the left surface is minus 16 newtons meter squared per coulomb. How about the flux through the back face of the cube? Well, in that case, the unit vector is oriented along the z-axis, but in the negative direction. Therefore, we can write that the area vector equals the magnitude of the area multiplied by minus k, which is the unit vector along the z-axis. Now, when you take the dot product between the electric field and the area, you have to take the dot product between I and k and j and k. These vectors are perpendicular to each other. Therefore, the dot product between I and k and j and k is always 0. And we get that the dot product between the electric field and the area is 0 in this case, which means that the flux through the back surface is 0, and similarly the flux through the front surface is also 0. In the last part of the problem, we need to find if there is charge inside the cube, and if yes, how much charge is there. Well, we calculated the flux through every single surface of this cube. If there is charge inside the cube, it means the flux cannot be 0. If there is no charge, then the net flux through the cube has to be 0. The net flux through the cube is calculated as the sum of the flux through every single one of its surfaces. So all we have to do is plug in the numbers. The flux through the top surface was minus 72, through the bottom was 24, through the right face was 16, through the left face was minus 16, and through the back and front faces was 0. The net flux in this case is minus 48 newtons meter squared per coulomb. Clearly, we have charge inside the cube because the net flux is not 0. Not only that, but because the flux is negative, you have to realize that the charge inside the cube is negative too. From Gauss's law, the net flux equals the charge enclosed in this cube divided by epsilon 0, and it is minus 48 newtons meter squared per coulomb. From there, we get that the charge will be equal to epsilon 0, which is 8.85 times 10 to minus 12, multiplied by the net flux, which is minus 48, and we get a value of minus 424.8 times 10 to minus 12 coulombs. This is the amount of charge that is enclosed in this Gaussian cube.